Hi everyone. So today we're going to look at combining phasor impedances. Now, uh, by the end of the session, you should be able to do this for series and parallel combinations. You should also be able to use these combinations to solve basic circuits for voltages and currents. And you should be able to describe what is meant by LC resonance, and we'll see what resonance is toward the end of the session. So, just to review, when we combined RLs and Cs, we saw that Rs in series added, just like inductors, and for the capacitors, they were product over sum, and it was the opposite in parallel. In parallel, we had product over sum for resistors and inductors, and we had them being added for capacitors. Now remember, this product over sum is only for two components. In reality, we have 1 over RT is equal to 1 over R1 plus 1 over R2 plus how many ever resistors we have, or how many ever inductors we have. But if we just have two, it works out to product over sum. So don't do that product over sum for more than two components. So when it comes to impedances, it turns out they behave just the same as resistors. It doesn't matter if it's R, L, or C. As long as you're working in impedance, they add in series, and we have product over sum for parallel. So even though the C, we have it the other way around, if we are looking at XC, which is the capacitive reactance, then in series it adds, and in parallel we get product over sum. So let's do a little example. We're going to calculate the current I by first combining capacitances and then combining impedances, and we'll look at the difference between these approaches. So first off, let's do it by calculating the capacitances. So since these two capacitors are in parallel, we will get C total is C1 plus C2, and then XC, which is the total reactance of these two in parallel, is minus J on omega CT, which is minus J on omega C1 plus C2. And if I find the current from that, which is simply V on XC, I get this, minus J omega C1 plus C2 V. So that's simple enough. I could do the same thing with combining the impedances, but this time, if I take XC1 is minus J on omega C1, XC2 minus J on omega C2, then to find the total impedance, I will have to do product over sum. So I multiply and add on the bottom here, and I have to go through all of this to reduce it to this form here. And we can see that that form here is the same as this form here. So I end up with the same total impedance and the same result at the end of the day, but I had to go through a lot more working. Now this isn't always the case. It is not that the working in impedance will always be longer. In fact, most of the times it's shorter. What I'm just showing you here is that to know when you combine first in with the capacitance of the components as opposed to the capacitive reactance, or the inductors as opposed to the inductive reactance, could shorten your working a lot. So you could imagine if we had inductors in parallel, it would be, or inductors in series, it would be easier to do or not inductors, sorry, capacitors in series. Then if I had capacitors in series, the taking the approach of adding one capacitance to the next first, I would have to go through the product over sum, and taking the approach of the impedances, I would just add them. So in that case, it would be much easier to work like that. So Let's do another example now, this time with an RLC circuit, and we're going to derive an equation for the current through the circuit and determine the value of the max current through the circuit. So I'm going to start this the same way. I'm going to look at what are my impedances. So I have XL, my inductive reactance, which is j omega L, and XC, which is 1 on j omega C. So, which is, in case you're wondering where the negative sign went, that is the same as minus j on omega C. So I'm going to add these, and I have the total reactance is j omega L plus 1 on j omega C. And if I turn that into a single complex number, if I combine them, I'll get 1 on omega squared LC over j omega C. So the total impedance, when I add the resistance to that, is R plus 1 minus omega squared LC on j omega C. So when would this become, when the current becomes a maximum is when the impedance is a minimum. So when would this impedance become a minimum? It would be when this term here goes to 0. If the value R is static, it can't ever change, but this value here could change based on the frequency. So when would this become 0? When this numerator is equal to 0, which means omega squared LC is equal to 1. At that point, ZT becomes R. We call this point when omega squared LC is equal to 1, or omega is equal to 1 on the square root of LC, the resonant frequency. And what that means is that J omega L, which is your inductive reactance, is equal to 1 on, or is equal to, sorry, J on omega minus J on omega C. Sorry, it will be equal to J on omega C. So in other words, when we add these two together, J omega L minus J omega C minus J on omega C, that will be equal to 0. So the inductive reactance cancels the capacitive reactance and make them seem like a short circuit. Even there's no real short circuit. So when that happens, you get the maximum current through the circuit. So this is what resonance is about. It's about the inductive and capacitive fields compensating for each other so that it makes it seem like they are not there if it's in series. If we have them in parallel, the L and the C this time, let's look at what happens. We're going to derive the minimum current through the circuit. So in this case, I go through the same thing, j omega L and 1 on j omega C. This time I have to find the parallel combination of these. So I put them product over sum for impedances, and I end up with the total reactance is j omega L over 1 minus omega squared LC. So we see here this time is the same, except we have the same resonant point, 1 minus omega squared LC, which means omega is 1 on square root of LC. Except this time when we have resonance, when omega squared LC is equal to 1, this time the impedance goes to infinity because we'll have j omega L on 0. So in this case, when they cancel each other, it makes it look like an open circuit and the current will go to 0. So I hope by now you could combine phasor impedances in series and parallel, and you've seen how to solve basic circuits for voltage and currents using this phasor analysis by doing these combinations. So we looked at the capacitors in parallel and then the series RLC arrangement, and you should be able to describe what is meant by LC resonance. This is the compensation of the inductive and reactive fields to either create the effect of a short circuit between the components or an open circuit.